once we're done, I'll have you do a drawing for me. That'll take up probably the last bit of class time. If for some reason you miss something or you don't quite get something right away because you were taking notes or you missed something, the slideshow is online for you. And then this recording that I'm making right now will also be online. So you can look at both as a resource. So make sure you have a pencil, paper out. If you want to take notes on Google Docs or whatever, that's fine with me. Just make sure you're not spending all your time on your phone. Please make sure your earbuds are out so that you can actually hear what I'm talking about. If you have any questions, please don't sprint to the front of the room. You can walk up to the computer, ask me your question so I know that I can hear it. If you're at home, just unmute yourself so I can hear whatever conversation you might have at home. Otherwise, if you don't want to, or you just don't have the want to ask a question in person, just send me an email and I will email you back as soon as I can with the answer to whatever question you have. As far as the project goes, I have almost half of them graded. I will have the other half finished today. If you have not gotten it graded or you have not gotten it back yet, please make sure to check that one, that it's turned in, and two, that I do have access to it. Some people that did picto charts or canvases, or there was another one. They sent me the link, but the link just takes me to, like, I want to create my own picto chart or create my own canvas, and I need to be able to see yours. So you need to make sure that I can have access to it, so I can when I get there, I can grade it, so I don't have to worry about trying to hunt you down later. So, classifying matter, how we actually take all of the matter and put it into unique categories that are specific to matter, atoms, everything that we're going to be talking about in this next couple weeks in chemistry. Does anyone have an idea on what this picture is? The picture I have on the board on the very first slide.
It's heat map of the source, or not heat map, UV radiation of the universe.
It is the radiation or the map of the universe. So if we look at this picture is an actual photograph representation of what our universe looks like. The universe is not infinite. It is expanding, but there are edges. There is a boundary to the universe. It doesn't keep going on forever like people for some reason think. There is an end, and there was a beginning. Where you see most of the light in this photo, the middle, that is where the center of the universe is. That is where there's the most stars, the most radiation. It's also kind of the location where that Big Bang happened. We took a particle that was extremely dense. It was infinitely dense, and it was infinitely small, and it just kept getting denser and denser and denser because something that has that much matter in it has a ton of gravity. Like our planet has a ton of mass, or is made of a bunch of stuff. The more stuff you have, the more gravity you have. The larger you are, the more gravity you have. And if you take something like the beginning of the universe, where you have something about the size of a marble, with all of the matter that we now have, all the stuff that we have condensed into the size of a marble, eventually it couldn't hold that force anymore, and it exploded outward. All of the matter that we have in this room, at the desk you're sitting at, the atoms that make up yourselves, the school, Somerset, the planet, our solar system, our galaxy, the universe, all of that matter came out of the Big Bang. From something as small as a marble, all of it came out of that one place. We have not created any more matter. all of the matter, all of the stuff, all of the atoms. When I talk about matter, we're talking about atoms. All of that stuff originated from the Big Bang. All of our atoms are as old as the universe itself. So the universe, if you don't know, is 13.7 billion years old, or roughly that. All of the atoms in your body, in all of those places I just listed, are 13.7 billion years old. Now, they can be reformed and reshaped, but the particles, the pieces of the atom, the subatomic particles, those are 13.7 billion years old. We can't make new ones. We can't destroy them. What we have is what we get. Does that kind of make sense right now? We're going to come back to Big Bang stuff later. But for now, when we're talking about matter, this is where we kind of got to start. If you're at home, can you just make sure you mute yourself so that you're not interfering with what I'm talking about? If you have a question, unmute yourself. But if not, please keep yourself muted. Here's just kind of another image of that, an artist's representation of what the Big Bang may have looked like. Now, this didn't happen. This was a very slow it happened instantaneously, and then we kept growing exponentially or very quickly right off the bat. So we're going to be classifying matter today. What are the different types of matter beyond just solids, liquids, gases, and plasma? So we're going to be looking at the composition of matter. If I'm moving too quickly, just let me know, and I can take a second. Remember that this slideshow is online, so if you need to come back later, or there's going to be this recording as well, so you can look at it either way, whatever you need to do. So the most basic category of matter, we can't get any more simple than this, is an element. The periodic table of elements, which I have shown on this slide, and we're going to focus a lot on this next week with the periodic table of elements, shows every single element that we know of. And the periodic table keeps growing, and as far as I'm aware right now, 118 is about where we're at. We might be at 123. New atoms are made, but in general, the most stable ones, the ones that are natural in the universe, are 1 to 92-ish. And I will talk about more about that later, so it makes more sense. But today we're not going to focus on that. I just want you to focus on the simplest type of matter is an element. And that means it's pure. We're talking about things like iron, gold, copper, zinc, hydrogen, oxygen. Those are all elements. Those, if we were to look at the atoms of that object. So if we looked at all of the atoms of a gold bar, and you were lucky enough for some reason to have a gold bar in your ownership, if we were to look at those atoms in the gold bar, it would be all solid gold atoms. There wouldn't be any copper mixed in. There wouldn't be any iron mixed in with the gold. It would be solid gold. That's what an element is. If we expand it a little bit, the next step would be a pure substance. So a pure substance is like a mixture of elements. So if we think of like salt is NaCl, which is sodium and chlorine. Sodium an element, chlorine an element, but when we chemically combine them or put them together, smack them together, we get a pure substance when we get a whole bunch of sodium chlorides, salt. When we get them, a whole bunch of them, keep adding together, and we get a large amount of it, that would be a pure substance. Now, if we had like water mixed in with that salt, okay, salt dissolves in water, but we can get salt water out of it. That would not be a pure substance because we have water, H2O, mixed with salt. If we have a pure substance, we have two or more atoms chemically combined, all the same. If I look at, there's that picture there that talks about some different types of pure substances. Water itself, if we have a glass of water and only water, that would be a pure substance. If we have baking soda by itself with nothing else in there, baking soda is a pure substance. a combination of multiple elements chemically combined, but all of those compounds, we call them, are the same compound throughout. So element, pure substance are the basic or the start of how we start to break matter down. Now we can take elements and pure substances and we can kind of break them down further. So a compound usually will go with a pure substance. We don't consider an element a compound. A compound is part of a pure substance, but it's when we have, like I said, two or more atoms chemically combined together. So like I couldn't physically pull apart H2 or hydrogen and oxygen in a water molecule or a water compound. I couldn't just pull the hydrogen and oxygen apart. I couldn't pull those two atoms apart. They're chemically combined. I would need to add a bunch of energy. So they're chemically combined together. They're stuck together, two or more atoms combined. A mixture, it could be a combination of elements or pure substances. A mixture is a little bit messy sometimes, literally and figuratively. A mixture is matter composed of two or more substances that can be separated by a physical means. So just quick show of hands. How many of you had a pizza last night? I knew there'd be a couple because pizza's awesome. Pizza is a mixture. I can look at a pizza and there are maybe you had pepperonis on your pizza. You can take the pepperonis off. I really hope your pizza had cheese on it, because if it doesn't have cheese on it, then it's not pizza at all. It's just bread with sauce. You can remove the cheese. You can remove the sauce. You can remove or take the crust apart. That's kind of a basic mixture, and there's different types of mixtures, but more or less, those are the basic pieces of a mixture. We have different compounds, different parts put together, different parts, different compounds. They're not all the same all the time. We can mix them together. So in a mixture, you have a combination of pure substances and elements. Different elements, different pure substances mixed together, which could be represented by a salad. Pretty much any food you eat. A lot of the drinks you drink are mixtures. So there are kind of two main types of mixtures that we can talk about. There is a homogeneous mixture. Homo, H-O-M-O, means one or similar or same or constant. And what this means, it's uniform. It's the same throughout. So if I think about a Gatorade bottle or a Gatorade drink, Gatorade is a homogeneous mixture. Can you take Gatorade and can I pull it apart? Like if I pour out one glass and then pour out a second glass and a third glass, are any of those glasses going to be different? No. They're going to be exactly the same throughout. They're uniform throughout. They're the same throughout. I can't separate a homogeneous mixture by using my hands and pulling it apart. I can't put it through a filter and filter out the different parts. A homogeneous mixture is the same. It's equal. It's uniform. It's not like a pizza where you might have 5 pepperonis on one piece and 10 pepperonis on another. It's not like orange juice if you have pulp in there, where you have the pulp and you have the orange juice and you can separate the pulp from the orange juice. A Gatorade is a solution, which means it's a homogeneous mixture. It's the same. A solution is just another way of talking about a homogeneous mixture. So if I say solution, I'm talking about a homogeneous mixture. We can also talk about like metals. Metals could be a homogeneous solution. Steel is a solution. Steel is a homogeneous mixture. You have a combination of carbon mixed with iron uniformly, perfectly, makes a super strong, super dense material that is hard to break and can support a ton of weight. An alloy is a metal that is a solution. Who could maybe think of a type of solution that you've drank or had today? Coffee would be a solution. I heard coffee. Coffee would be a solution. You can't separate it. It's uniform. It's the same throughout. You don't take a drink of your coffee and the first drink tastes like all sugar. And then if you add milk into your coffee, the next drink doesn't taste like just milk. It's spread out. It's evenly distributed. If you had apple juice, same thing, homogeneous mixture. Anyone in metals? Anyone taking metals or welding or so any of the metal you're using, I doubt you're probably not using just straight iron or just pure iron. You're probably using an alloy, a mixture of metals or a mixture of carbon and a metal that makes it strong, not brittle. Like iron by itself is super brittle and it's strong, but not super strong. So these are things we use all the time that have been engineered by scientists and by our society through human history over the last thousands and thousands of years that are super useful to us. Now we have the other type of mixture, the opposite of a homogeneous mixture, and this is a heterogeneous mixture where I come back to that idea of a pizza. This is where you have multiple parts, multiple compounds, different pure substances, different elements that are unevenly distributed in a material, in matter. This is something you can physically separate with your hands or by a physical means. Like I could boil, like if I had, let's say, like the picture shows, I had oil mixed with water. I don't know if you guys know this, but oil is less dense, meaning it floats on top of water. You could physically pour off that oil and separate the water from the oil. It has two clear parts or two or more clear parts, and you can separate them with your hands or by siphoning off the oil. You could take a paper towel, and the paper towel could soak that oil up and leave you with the water behind. If we think about a salad, I don't know if people like large salads, but you could have tomatoes, cheese, onions. Some people like peppers in their salads, mushrooms, so whatever dressing you like. You can take out and remove the different pieces. So like if you don't like mushrooms, like a lot of people don't, you can pull those mushrooms out. No problem. Throw them away. Now you have a mixture minus mushrooms. Don't like tomatoes? Great. Take the tomatoes out. Maybe it's not the right type of cheese. You can separate those parts out. This mixture is not uniform. It is different. Every time I take a handful of trail mix, if my trail mix has M&Ms, peanuts, almonds, cashews, raisins, whatever you have in a trail mix, you take your hand into that bowl of trail mix. Every time I take a handful out, it's probably not going to be the same. I'm going to have a different amount of M&Ms. I'm going to have a different amount of cashews, different amount of peanuts. That comes with being a heterogeneous mixture. Any questions so far? Pretty simple stuff, guys. Not super complicated yet. Stop me if a question comes up. Now we're going to get into different types of heterogeneous mixtures. So there are some liquids that look like they could be a solution or a homogeneous mixture. Chocolate milk is a great example. If you let chocolate milk sit long enough, the chocolate or the chocolate particles will fall out of suspension or fall out of the liquid and separate from the white milk and the chocolate particles. So you'll get two different parts. A suspension is a type of heterogeneous mixture. There are two parts. You might not be able to tell right away, but eventually they will separate. If you buy like Nesquik or Ovaltine and you mix those at home, you can see this. The chocolate doesn't perfectly mix with the or the white milk. You can stir and stir and stir, and not all of it's going to separate. That's a great example of a suspension. If you buy like Kemp's or True Moo or whatever Land O'Lakes chocolate milk is called, might be that's True Moo, I don't know. But with those types of chocolate milks, there's additives. So I might ruin chocolate milk for you right now. So I apologize if I do, but chocolate milks that you buy in a gallon at the store have a kind of interesting material added into it to keep the chocolate from separating from the white milk. A lot of those companies add algae to the chocolate milk to the chocolate and the white milk separate.
I eat algae and love chocolate milk.
Who doesn't like algae? But yeah, they added in the algae helps the chocolate stay in suspension so you don't see it fall out, because no one's going to buy a gallon of white milk with chocolate milk at the bottom or chocolate powder at the bottom.
I would.
Yeah, I don't think so. If you're ever playing in a mud puddle or when you were a kid, and for some reason you were a kid that never played in a mud puddle, can anyone raise their hand and tell me they never played in a mud puddle? Put your hand down, Zach. I know you played in a mud puddle. A mud puddle is another great example of a suspension. You have all those dirt particles. You have water. If you're playing in the puddle, they mix up. The water gets really dirty, really murky. And then if you leave that puddle long enough after playing with it and go back later, it will have settled back out. It's going to take some time, but eventually it will. You can have a colloid, which is a type of heterogeneous mixture. It's very similar to suspension, only a colloid won't separate itself out on its own. It stays in suspension. It stays floating, mixed together in the liquid. The only way you can tell a colloid from a suspension or a solution is if you shine a light through that liquid. And I'll show you an image of what that looks like, because when you shine a light through a colloid, you can see the beam of light through the liquid. So if we took milk, white milk is a colloid. It is a type of heterogeneous mixture. If you took a flashlight on your phone or a regular flashlight and shine your light through it, eventually, or you would be able to see a straight beam of light through it. Paints quite commonly are colloids that you can do this as long as you have bright enough light. Well, I had a picture of it somewhere. I will find a picture of this and show it to you later. But what I would encourage you to do is take a moment once I'm done talking and Google what a colloid is, and you're going to find an example picture of that solution, that heterogeneous mixture with a light being shined through it, so you can see what that is or what that looks like, so you can help identify what kind of mixture that is. This week, or later this week, I think Thursday, it might be Friday, we're going to be doing a lab where you're separating mixtures. And what you're going to need to think about is, okay, how do I separate a heterogeneous mixture? how can I separate a solution or a homogeneous mixture? If I'm given a beaker with a bunch of different types of elements, pure substances, and mixtures put in there, you're going to have to figure out and think about how I can separate those things using these ideas. So that's something you'll be doing in the future. You'll need to think about how I can separate different types of classifications of matter. Because some of them are pretty easy. Some of them you might need to think a little bit, but that's okay. What I am going to have you do after this question, can I create or destroy matter?
No.
No. I could throw it in a fire. I could smash it with a hammer. I could run it over with my car. I cannot destroy matter. I could take a Death Star and blow up an entire planet with the Death Star. The matter is not destroyed. It's just changed. It looks different. It's changed. Matter can't be destroyed. So what I want you to do is I want you to make me a quick chart. You can do this on scratch paper. You can do this using Google Draw. You can, if for some reason your Chromebook still has Paint on it, like the software Paint, whatever you want. If you want to make it in a Google slide, fine. I don't care. I want you to make me a simple chart that has the different classifications of matter in it and how they're connected. So like I would tell you right now, the very first box on the top of this chart should probably say matter. And then from there, you might split it off and put the two different types of matter we first talked about. So if you look at these slideshows that I've attached and what we just talked about, you can put terms in a chart that represents the different types of matter that we've looked at today. So please make sure that your chart includes elements, mixtures, compounds, pure substances, matter, homogeneous mixtures, and heterogeneous mixtures, suspensions, and colloids. Okay? Make sure all of those words, those vocabulary words are used in this chart. And then give me like an example. So go on Google and type in what's an example of a colloid. And give me a picture of that colloid next to it. So if you're doing it by hand, draw me a quick jug that says milk on it next to colloid if you're doing it on a piece of paper. Doesn't need to be super fancy. Doesn't need to be life-changing. Once you make this chart, I would ask that you hold on to it. Do not lose it. When I come back, I will ask you to pull that chart out so I can look at it and see what you got. And then any like quiz or test, if you choose to go that route down the road, or if you want to use it on a project or whatever you need, you can have it there for you, or a lab will be there to help you. It'll be a resource for you. So take this time and put this simple chart together for me with these important pieces that I've just talked about. Add some color, make it look nice. Don't rush it so that you don't have to, down the road, you don't go to look at it and you can't understand what you were talking about. If there's any questions, I'll be up here on the board. I'll leave this slide up with me so that you can see what's going on. But I'll be right here. So go ahead, get to work.
I need to kind of take a attendance here real quick, too. So